Okay, this lecture covers Module 8, entitled The Network Layer from your curriculum. So if we start into that, as always, we start with a brief statement about what we're going to learn in this module. And in particular, we're going to learn about the network layer, which is layer 3 of the OSI networking model, and various protocols that we have at layer 3. In particular, down here in 802, we're going to learn about how we have IP protocols for reliable communications from source to destination. We'll talk about the format of an IP version 4 packet. We'll talk about the format of an IP version 6 packet. We'll talk about routing, which is a very important thing that occurs at layer 3. And then related to that, we'll talk about routing tables that live within routers that dictate or help facilitate the routing of IP packets from their source to their destination. So here is the OSI model again. Basically, we're at layer 3. Layer 3, if we're encapsulating, is going to take information from layer 4, encapsulate it into IP version 4 packets, or IP packets, maybe could be version 6. That will pass them down to the data link, which passes them down to the physical layer for it to go. So layer 3, as with all the other layers, interacts with the layer above and below. Some of the things that we'll talk about is the addressing of end devices, which will be IP addresses. We always talk about encapsulation as things move down the layers of the OSI model. So we'll talk about encapsulating into IP packets. Routing is the process of making sure that packets can make it from their source to their destination. So we'll talk about routing. And then when they make it to the destination, they de-encapsulate, as always, passing it up from layer 3 to layer 4. This is an animation. I think we've seen it a number of times. So basically, we're communicating between the IP address on the left, the IP address on the right. So it shows the PDUs. We have data that's broken into a segment. That segment is then encapsulated into an IP packet, which is encapsulated into an Ethernet frame, and then that frame is converted to binary, ones and zeros, sent across the network. That frame is read, it is de-encapsulated, which extracts the packet out of it. Then we de-encapsulate, we get a TCP segment, and then that recreates the data for the three higher level layers. So that's the encapsulation process as we move down the OSI stack on the left, and de-encapsulation as we move up the layers on the right at the destination. So as we talked about and have seen before, we take a transport layer PDU, which is a segment, and then we're going to encapsulate that into an IP packet. And of course, encapsulate, you've heard a number of times, means adding a header and possibly a trailer to the higher level information coming down the stack. These are going to, well, let's see. They talk about NAT here, network address translation. That's something we'll talk about later. That's important for example at home, having a single public IP, going through your multifunction device, and then having a bunch of private IPs on the other side, yet those private IPs through NAT are still able to talk to devices on the internet, capital I. There are three primary characteristics of the internet protocol. We'll mention them briefly, and then we'll talk about them in more detail. Connectionless means we do not have an established connection that exists the whole time a communications is going on. The fact that at IP we have best effort as opposed to guaranteed delivery of packets. We'll talk about how to handle that when we talk about the transport layer. And then media independence. We'll talk about what that means in the case of internet. So as far as connectionless, a lot of times we use an analogy of the postal system. I think we've done that at least once before. But this kind of demonstrates connectionless. So we have somebody on the left who's sending a letter to somebody that resides in the house on the right. The letter makes it there. It makes the mailbox. It goes over through trucks and planes, makes it to your city, then makes it to your postal carrier who brings it to your house. Now, this is best effort. Most of the time the letter makes it there, but occasionally the letter may become lost. So it is not guaranteed delivery, which is something we'll talk about in a moment. When the person sends the letter, they don't know exactly when it's going to arrive at your house. They don't know if you're going to be at home when it arrives. You don't know the letter's coming, even if the person said, hey, I'm going to send you a letter, or I did send you a letter. You may or may not know exactly when it was mailed, but you may have a guess as to what day it might make it to your house. But in reality, you don't really know when it's going to get there. So now if we look at the network, it's kind of the same thing. We don't know when a computer is going to send a packet to us. We as the sender assume the packet's going to make it to the destination. That packet travels through some set of network devices and then hopefully makes it intact to the destination computer. So there's a lot of similarities there between that and a letter being sent through the U.S. Postal Service. As far as best effort, hopefully it makes it there, hopefully the network's up, but we really have no way to know. So here, the sender sent 3 packets, and only 2 of them, for some reason, made it to the destination. So at the layer 3, at the IP layer, we don't really have anything to compensate for that. Also, the packets may have arrived in a different order than we sent them. So those are a couple things we'll have to address at layer 4. As far as media independence, we kind of saw this in a previous module where they were sending a frame. The frame went over Ethernet, it went over wireless, it went over a satellite, I believe. I think it went over a frame relay link. But the whole point was everything that we were passing along those links was a frame. So when we're talking about layer 3, everything's a packet. So if we have an Ethernet connection, we send an IP packet. Then that may go over a serial link. It's still a packet. May go over fiber optics, still an IP packet. May come down Ethernet. May go wirelessly to the destination. All those are, it says packet, packet, packet. Everything at layer 3 is an IP packet. And IP was designed so that it could work over different types of media. There may be new medias to come in the future that they will use Ethernet over. It was designed to be flexible. Um, 817 is a check your understanding on the characteristics of IP protocol. So you can do that on your own. And we'll move on to 8.2, talking about IP version 4 packets. So we have a header that we place in the IP packet when we encapsulate the segment from the layer above. And in brief, the purpose of the IP packet header is to get the packet from the source to the next hop. And the next hop is the next device, the next router it needs to go through to make it to its destination. And finally, it will make it, hopefully, to its destination device. So here we have the fields of an IP version 4 packet. The first thing we have is 4 bits, which is the version. So in the case of version 4, those bits would be set to 0100, which is the binary representation in 4 bits of the decimal value 4. We have a length of the header, and then we have different information in here. The main thing they want to talk about is the version and the source IP, which is 32 bits, 4 bytes, and the destination IP address, which is also 32 bytes to live, or 32 bytes in length. The only other couple of things I want to point out is the header does have a checksum to make sure the header arrived intact. Just like when we talked about frames, we talked about the frame check sequence, which was a checksum to make sure the frame arrived intact. And then also we have this time to live thing. Basically, this time to live starts at a value around 255, and then it will, every time it goes through a router, be decremented by 1. If that value ever makes it to 0, the packet is thrown away, and the assumption is we're in some type of loop and the packet's never ever going to make it to its destination. So they talk about some of the fields down here. You can go through and look. You also have numbers for protocol. If it's a TCP packet, it will be a 6. If it's ICMP, which is what ping and traceroute use, it'll be set to 1, etc. This is a video that shows you some of the things from an IP version 4 header by using Wireshark. I think this is very valuable. It's 5 minutes and 20 seconds long, and I do intend to play it here within the lecture.
I have a screenshot from a Wireshark packet capture, and you can see that the second packet that's been captured has been highlighted, and then in the packet details window, the network layer information has been expanded to show us all of the things happening at the network layer. So let's see what's happening in this particular packet that we're examining. We can see that, first of all, the network layer protocol or internet layer protocol that we are dealing with was Internet Protocol version 4, IPv4. We can also see that the source IP address was 192.168.1.109. You can see it also highlighted up here in the packet list window area, and that the destination IP address was 192.168.1.1, and we can also see that up here. We can see that at the higher layer, this is a TCP protocol packet, but if we limit ourselves to just the IPv4 fields or the IPv4 information, we can see the different types of control information that's contained in every IPv4 packet. For instance, the version number, which is 4, identifying this as an IPv4 as opposed to IPv6 packet. The header length, or the length of the header, this is the minimum size of an IPv4 header. The differentiated services field, which is used for packet prioritization and is useful for applications like voice over IP. The total length of the packet. The identification number, which is used for fragmentation. The flags, you can see that the DF bit has been set, which stands for don't fragment. This packet is not large enough or is not identified for fragmentation. Fragment offset. The TTL, or time to live, which is set to 128. Every time a packet is routed from one hop to the next, the TTL number is reduced. When the TTL number reaches 0, the packet is dropped, ensuring that packets don't circulate on the internet forever on an endless loop. The TTL value is also used in ICMP trace routes and pings. The protocol field lets us know the type of information to expect in the data portion of the packet. A 6 identifies the data portion of this packet as being a TCP packet. The header checksum field, which allows routers to check to see if there are any errors or inconsistency in the IP header. If there is, the packet will be dropped. And then lastly, the source and destination IP addresses, which are the most important part of the IPv4 packet. let's take a look at 2 more screenshots of Wireshark packet captures, and we'll see some similarities and differences. The next screenshot shows us that now we're looking at the 8th packet captured. The packet's source IP address is also 192.168.1.109, and the destination IP address is 192.168.1.1, except this packet is an HTTP GET request. So this is a request to a web server located at 192.168.1.1. You can see that the network layer or internet layer information has been expanded, that it's also the IP version 4 protocol, and that we have similar information in the different fields. Notice under the total length field that this packet is 411 bytes compared to the previous packet, which was only 52 bytes. You can tell that this packet has a lot more information, or is a much larger packet than the previous one. If we look below the Internet Protocol version 4 information, we can see the TCP information, and then below that there's Hypertext Transfer Protocol or HTTP protocol information in this packet as well. I'll move forward to the next packet, and you can see that this packet is the 16th packet captured right up here. It's also from host 192.168.1.109 to host 192.168.1.1, except this is the ICMP protocol. You can see from the information in the packet list window that this is an echo or ping request. If we look in the Internet Protocol version 4 information in the details area, we can see some minor differences. The version is still 4, the header length is still 20 bytes, but we can see that the flags are slightly different, and that the protocol field is now set to 1, indicating that the data portion of this packet is an ICMP protocol message. Notice that in the details window at the bottom here is an expanded area to look at the header information specific to ICMP.
Okay, as hopefully you realize, Wireshark does a lot of things for you. It takes information that's traveling across the network, it divides it into the particular layers of the OSI model. It does things like take the 32 bits of the IP address and put it in decimal dotted notation for you. It breaks flags apart, tells you what the flags are set to, tells you their decimal value, for example, on the version. Does a lot of things for you that if you were having to go through and try to decode that quote by hand would be very, very difficult. So 824 is a check your understanding on IP version 4 packets. You can do that on your own, and we'll move on to 8.3 talking about IP version 6 packets. The reason we have IP version 6 is we, depending on how you look at it, have either run out of IP addresses or about to run out of IP addresses. So that is the primary reason. The first one there that says IP address depletion. Technically, the top level IP addresses were exhausted or completely given out in January 30th of 2011. Those were assigned to different regional registrars for different countries or different areas of Earth, and depending on how quick they gave them out, they ran out a little different. So Asia Pacific ran out in April 2011. Latin American and the Caribbean ran out in June of 2014. North America ran out in September 2015. Africa ran out in April 2017. Europe, Middle East, Central Asia are grouped together. They ran out in November of 2019. Now, individual ISPs that were assigned to addresses may still have unassigned IP addresses in that to give out. And You can also, if an ISP doesn't use numbers, they can give them out and they can be reassigned either by that ISP or a different ISP. So that's why, it doesn't seem like we've run out of addresses, but we're really close. And part of that is because the way they're assigned is really wasteful, and we haven't really talked enough to talk about that. One analogy I talk about here is a while back we ran out of telephone numbers. Used to, area codes their middle number had to be a 0 or a 1. Back a long time ago, Kentucky was simply 502, and in the western part of the state, and 606 in the eastern part. But if you think about it, within a particular area code, you have 7 digits for possible number combinations within that area code. So basically you have 10 million phone numbers. There are some cities that have more than 10 million people in them. Some people have, multiple phone numbers these days, several cell phones, maybe a landline, maybe a fax machine. If your car has OnStar, it has a telephone number, etc. So we used up all the phone numbers that we had available to us. So they went back and changed some of the rules. For example, they lifted the restriction that the middle of an area code had to be a 0 or a 1. So what happened in Kentucky, we got 270 and 859. So if we look at the eastern part of the state, they used to be 502. Basically, Louisville took 502 because it was the most populous city, had the most businesses, and that would minimize the number of people who would have to change their area code, possibly print new business cards, get new letterheads, print new ads, etc. And then the rest of the western part of the state got 270. At first, you might think that Lexington kind of did the same thing. Why didn't Lexington keep 606? Obviously, we didn't. And the answer is not because we were being nice, knowing that eastern Kentucky, being a rural area, might not have the money to, or it might be a hardship for them to change business cards, letterheads, etc. But I've not had anybody, when I ask why is Lexington 859, have a guess. But the reason is if you pull your phone out and look at what 859 spells, with the letters on there, it spells UKY. So Lexington is 859, which spells UKY. So that's the analogy of running out of phone numbers to running out of IP addresses. A couple other things that IP version 6 dealt with is, I briefly talked about NAT before. You can't directly get to a machine from the outside world. The address has to come from the inside and be NATed, and then you can talk back to that machine. We'll talk about NAT in good detail later, but basically they eliminated the need for NAT and allow, because they have so many IP version 6 addresses, every device to have a public IP. So they basically did away with the need for private IPs. The other thing is increased network complexity. They said NAT extended the lifespan of IP version 4, but it was only meant for a transition period until we can make it to IP version 6. So IP version 6 has been around since the early 90s. They knew some problems were coming, and they did that. So the engineering task force, IETF, basically came out with IP version 6. Now, there was an IP version 5 that primarily dealt with quality of service, and it was never really released. So, IP version 6 is out. IP version 4 was out for decades. IP version 6 will probably be around just as long, if not longer. But at some point in the future, there may be an IP version 7 that will be the next version that comes out. So some of the improvements were increased address space. We have a comparison down here, but basically we went from a little over 4 billion IPs to this big, huge number here, 340 undecillion addresses. So that's a pretty big number. They say it's roughly equivalent to every grain of sand on Earth. That didn't really mean a lot to me, so I did some calculations. And basically, if you take a square meter of the surface of Earth, either on land or in the water, IP version 6 has so many IP addresses that every square meter of Earth could have 0.6 million billion addresses. So, may not still be a great representation, but to me, I think that's a little better than the number of sands on Earth. They simplified the IP version 6 packet to make it more efficient in the handling. And like I said, NAT was intended for a transition period to allow us to keep using the internet even though we were running out of addresses. And IP version 6 no longer requires that. The next section is IP version 4 packet header fields in IP version 6 packet header. I couldn't really make a lot of sense out of that. I think a more appropriate title would be something like IP version 4 header versus IP version 6 header. Here it sounds like you're putting an IP version 4 header and an IP version 6 header. And even though we will at some point in the future talking about putting an IP version 4 packet inside an IP version 6 packet, it has nothing to do with putting the header in the header. So here we have a representation 4 bytes wide, of the IP version 4 header. If I scroll down here, we have the same 4 bits wide. Physically, the packet looks to be the same size, but most of that is because we went from 32-bit addresses to 128-bit addresses. Notice that there are very few fields in the actual header of an IP version 6 packet. So, destination IP and source IP are pretty obvious. The hop limit is basically the replacement for the time to live. How many hops can this do? We have something that had come about referred to as a flow. And I've told you that if a message is going from source to destination, it's usually many packets. Thousands, tens of thousands, however many is needed. One conversation between a source and destination is known as a flow. And we can actually name those flows so that if we were doing monitoring or some statistics of network traffic, we actually have meaningful flow names. Just like we had video on IP version 4 headers, here's one on IP version 6 headers. It's almost 6 minutes long, but I think it's important, so I am going to play this within the lecture.
This screenshot shows a packet capture using Wireshark and the network layer information from an IPv6 conversation. Let's take a look at it. In this screenshot, we can see that the highlighted packet is packet number 46, and that the source address up here in the packet list window shows that it is a global unicast IPv6 address. You can see this starting with the 2001:6F8. The destination address is also a global unicast address, 2001 6F8 900, and so on. And if we look over in the protocol field, we see that at the upper layers, this is a TCP packet, and that it's an attempt to establish an initial communication with an HTTP web server. If we look down in the network layer information area, you can see that the IPv6 information has been expanded. Let's take a look at some of the protocol field information for Internet Protocol version 6. First of all, you can see that the amount of information in the IPv6 header is much smaller than in the IPv4 header. Now, there are some interesting features. For one, you can see that the version field is the same. In this case, it says 6, identifying this packet as IPv6. We can also see the binary 6 here. The next field is the traffic class field. The traffic class field serves the same function as the differentiated services field in an IPv4 packet. It handles traffic prioritization and congestion. The next section you can see is the flow label. The flow label field is a new field for the IPv6 protocol. Its purpose is to maintain the same packet flows through routers and switches so as to help real-time applications that need packets to arrive in the same order. You can see the next field is the payload length field. This is the same as the total length field in the IPv4 header. This field tells us the total size of the packet, in this case 40 bytes. The next header field serves the same purpose as the protocol field for IPv4. You can see that it's identifying that the upper layer data portion of this packet is a 6 or TCP. The hop limit serves the same function as the TTL field in an IPv4 packet. You can see that the hop limit currently is set to 64 hops. Once this decrements to 0, the packet will be dropped. Next, we have the source IPv6 address, the destination IPv6 address, and then at the upper layer, we can see that this is a TCP packet with TCP header information. Let's take a look at the next screenshot. In the next screenshot, you can see that we've now highlighted packet number 49, and now we have a connection with this web server. This packet is now a GET request to the web server. If we look down in the expanded Internet Protocol version 6 packet details window, we can see that the payload length is a lot larger. We can see below the IPv6 information, the TCP information, and that now there is HTTP protocol information as well within our GET request. This is our GET request to get a web page. If I go to the next screenshot, the last screenshot shows an ICMP version 6 neighbor solicitation message. If we look up in the window at the highlighted packet here in packet number 1, we'll see that the source address this time is not a global unicast IPv6 address, but a link local address. We can tell that from the FE80 here. We can also see that this link local address used EUI64 to resolve the interface identification portion of the address. We can tell that by the FFFE within the address. The destination address is an FF02 IPv6 address, indicating that this is a multicast packet. If we look over at the protocol, we see that it's ICMP version 6, and then information about the packet tells us that this is a neighbor solicitation message for the same device that we were contacting in the earlier screenshots. The function of this packet essentially is similar to an ARP request in IPv4. We need to discover the link local address of this device, so we send out an ICMP version 6 neighbor solicitation message, multicasted, and we're hoping to get back a link local address from this neighbor. If we look down in the expanded details window, we can see the version is 6, traffic class flow label, payload length, which is the entire length of the packet, the next header field, which is like the protocol field in IPv4, indicating a 58 that this is an ICMP version 6 message in the data portion of the packet. The hop limit, 255 hops. This is similar to the TTL field. and then the source link local address and the destination multicast IPv6 address. At the bottom below the IPv6 information, we can see that there's an expandable area specific to the Internet Control Message Protocol version 6.
Okay, and section 836 is check your understanding on IP version 6 packets, so when you're ready you can do that on your own. We'll move on to 8.4, which is talking about routing. And before I start into this, one thing that they haven't really mentioned in this curriculum that in older curriculums they used to talk about pretty early on is some of the networking devices operate at particular layers. So we're getting ready to talk about routing, which is performed by a piece of network equipment called a router. And we say that a router is a layer 3 device because it operates on layer 3 information such as IP packets. At layer 2, switches and bridges are layer 2 devices, and then the media, NIC card, and other things like that are layer 1 devices. Okay, so I just want to point that out. So talking about forwarding decisions, which will ultimately possibly become router decisions, is when we send a packet, that packet is destined for one of 3 locations. It's either destined for itself, so it's going to stay on the device. I have a little issue with saying localhost because the device, when you talk about itself, is referred to as localhost. So I would really change that to a localhost, or a host on the local area network would be more accurate. Or it's destined for a remote host, which would be a host or device that is on another network. The way we determine where this is going is based on the subnet mask, which they mentioned down here. We'll talk about subnet mask and something called network math in quite a bit coming up. But right now, let's just say that the net mask is what divides an IP address into the network it's on, and then a unique host on that network. So up here they're showing the network, which is 192.168.10.0/24. So that means the division point is right here at this decimal point. So the network is 192.168.10.0, and then a particular host, for example, the interface on the router for this network would be 192.168.10.1. So that's what they're showing us here. They're showing us the network number, and then without writing out the whole thing, telling us the specific host or specific IP on the network. Okay. The next thing we talk about is something referred to as the default gateway. The default gateway is the device that we use to talk to or get a packet to hosts that are on a different network. The default gateway has an IP address that's in the same address range or on the same network as all the hosts within that subnet. It's going to accept data and from the local network and make routing decisions to send it to its next hop, which is the routing of traffic to other networks. Default gateway may sometimes be called default router. It may be called the gateway of last resort. Basically, if you don't know what to do with a packet, send it to the default gateway, and the default gateway router will make sure it makes it to its destination by sending it to the next hop. So here, they're showing that same graphic basically. If you're on this LAN within this network bubble or cloud, the devices are going to talk to each other. The router doesn't need to forward the traffic. But if it's going to another network, it's going to send it to the default gateway, which is 192.168.10.1. The router will then use something called a routing table to decide where to send that to get it to the appropriate remote network. I think I mentioned this once before, but often the interface on the router is .1 within the local network. It does not have to be .1. It could be anything. I worked with a router recently that used .254, the highest address instead of the lowest, but .1 is a very common thing to use as the gateway just because it's easy to remember and easy to tell people. Now then, when you send something, whether it be out the local host, which we're going to discuss first, or through a router, it's going to use something called a routing table. So in this window, we have a command prompt on PC1, and the command to look at the routing table is netstat space -R, and this is what it tells you. Basically, it learns most of this information, and for example, it says if you are trying to get to 192.168.10, which is the network I'm on, it's on link, which means it's on the local area network, and you do that by going out my NIC card, which is 192.168.10.10. Now then, if you don't have an entry for the network you're going to, then you're going to use the default gateway, which is represented by 0.0.0.0 in IP version 4 with a net mask of all zeros. The gateway is 192.168.10.1, so it is right here. That's where we're going to. And the way we get to that is by going out my NIC card that has IP address 192.168.10.10. So that will route the packet to the default gateway. It will look at its routing table, which we're getting ready to, I guess we'll see that later, it looks like. But it'll have a similar routing table. So 845 is how a host routes. Check your understanding on that, and you can do that on your own. And then we'll move on to the introduction of routing, which is going to talk in more detail about the actual routers. So, packet forwarding decisions. Basically, we have packets to send, and in this case, we have a packet that is being sent. It is going from the destination is 10.1.1.10, which is over here, this PC. So it's going to have to pass through a couple of routers that will have to make routing decisions to get it there. So what happens is it'll go into this router. It will look at its routing table, which is shown down here. It has a route entry that says if you're going to 10.1.1 network, which we are, then we do that via router 2. So that packet comes into this router, goes out this interface, goes to router 2. If we look at router 2's routing table, it's basically going to say if you're going to 10.1.1, go out this interface of the router, and when it goes out that interface, it will ultimately make it to the destination PC. So basically, it's going to look at the IP header information, compare it to its routing tables, make routing decisions, which tells it which interface to go out to make it to its next hop. In the case of routing tables, it'll keep track of things that are called directly connected networks. Those are networks that are actually plugged into an interface on the router. You have remote networks that are networks that are not directly connected to you, However, you have information on how to reach those networks by sending it to its next hop. And then we have a default route, which basically means if you're not going to somebody that's listed in my table, then here is your next hop to go to. Routers can learn things in two different ways. You can manually or statically enter the information, or you can dynamically learn that information, and we'll talk about both of those, starting with static routing. So in the case of static routing, someone went into the device, it could be the PC, but in this case they're showing us the router, and actually said IP route. If you're going to this network using this net mask, here is the address of the next hop router, or this is the router you should go to. So you went in and manually or statically entered that into the routing table. The problem they're showing us here is if we told this router to statically always go to router 2, and this route goes down, then for this to get corrected, let's assume this can't be fixed quickly. Somebody dug through a piece of fiber or something. Somebody has to notice that we have a problem. They have to know that we have a static route on router 1. They have to go in and change that static route to now go to router 3. And then when this connection gets fixed, if they really want this to be the default route between these two, then they would have to go in and correct that. Down here they're saying this is appropriate for small networks. That means in a huge network it would be really difficult to configure this, keep track of it, and fix it when we had a problem with a particular route. Now in the case of dynamic routing, we use protocols that are talked about in Cisco 3, such as OSPF or EIGRP, that will share routing information and what networks they're connected to, what networks they know about, etc. So they basically exchange that information, and that is referred to as learning a route. The other nice thing about dynamic route is the same thing. If this route goes bad, dynamically, very quickly, router 1, 2, and 3 can change their routing tables so that we route through router 3 to go between router 1 and 2. When this is fixed, if this is the best path, then it will very quickly switch back to using the best path. So 855 is about a 6-minute video on routing, but I think it's important, so I am going to play that here in the video.
A router uses information in its routing table to forward packets. A routing table displays entries listing all the networks that a router is aware of and the best path to reach them. It is very important to be able to read and understand the entries in a routing table. In this demonstration, we'll take a look at a router's IPv4 routing table in detail. But first, let's examine the network topology. It actually consists of 5 separate networks or subnets. There are 4 LANs, 2 connected to each router, and 1 WAN connection between the 2 routers. If we look at R1, it has 3 directly connected networks. Network 192.168.1.0 connected to interface G0/0/0. Network 192.168.2.0 connected to interface G0/0/1, and network 209.165.200.224 connected to interface S0/1/0. R2's LANs are not directly connected to R1, therefore they are considered to be remote networks as far as R1 is concerned. In order to forward data to remote networks, a router needs to learn about them first through the use of static or dynamic routing. In this example, R1 has learned about them through the dynamic routing protocol OSPF, which has been configured on both routers. To view the IPv4 routing table, I'll click on router R1, and from the CLI tab, I'll press Enter to connect to the command line. From here, I'll type enable and press enter to enter privilege exec mode, and from here I'll issue the show IP route command to view the routing table. If I press the space bar, I will see the full output. At the top of the output are letter codes that indicate how each network, aka route, was learned. This is referred to as the route source. Underneath that, we can see the routing table entries. These represent all the networks that R1 knows about and the best way to reach them. Let's further examine some individual entries. First, let's look at the entry for network 192.168.1.0. The letter C in front of the entry is the route source and indicates that the source of this route is a directly connected network. And you can also see that in the entry here. Gigabit Ethernet 0/0/0 is the interface to which that network is connected. Now let's look at the entry for network 10.1.1.0. This entry has a route source of O, which indicates that it was learned via OSPF routing. After the network address, you can see two numbers in brackets that are used by the router to help determine the best path to the network. The first number is the administrative distance, which indicates the trustworthiness or preference rating of one route over another. Next is the metric, another value used by the router to help determine the best path. The metric may be calculated using hop count, bandwidth, or some other factor. This network is reachable via this next hop address, which represents an interface on router R2. This is a timestamp that tells us how long ago this router last received an update on this route. And serial 0/1/0 is the exit interface on R1 through which to send the packets. For the purposes of this demonstration, you can ignore any entries that do not list a route source at the beginning. These are basically headings. Also note that for each directly connected network, you have an entry below it with a route source of L. L refers to a local route, and basically this is the IP address of the interface to which that network is connected. This routing table shows that R1 is aware of all 5 networks present in the topology. It has 3 directly connected networks, it has 2 networks that are remote and were learned through OSPF routing. And lastly, if you look at the last entry in the table, you will see a statically configured default route. This manually configured route can be used to forward any packets that don't have a specific entry in the routing table. The purpose of a default static route is so that the router will not drop any packets. These are just some of the basics of an IPv4 routing table.
Okay, 856 is entitled Intro to an IP version 6 routing table. So we're on a particular router. In this case, we see it's R1 from the prompt. Also, it is highlighted up here in the graphic. The show command gives us information. Show IP means we want to see something about Internet Protocol, and route means we want to see the routing table. So it goes through, it has a whole bunch of codes up here at the top. S means we have a static route. So here is a static route. We have other learned addresses. The O means it was learned from OSPF. C means it's directly connected to us. L means it's local. So we have this again, it tells us whether it's directly connected or not, and tells us which interface to use to get to the destination network. So that's how we do it on a router. 857 is a check your understanding on your introduction to routing. You can do that on your own. That finishes up the new material in this module. So, what did I learn in this module? Short version is we learned about layer 3, the network layer, and here's the things that we read in particular. You can read through that on your own. And then 852 is the module quiz on the network layer, which you can do on your own as well. So that concludes the Module 8 lecture.